So in our last class we practiced factor trees, and those are going to play a big part in what we're going to do today. We're going to simplify square root expressions. So the first thing I want us to do is recall what perfect squares are. A perfect square is the product of a rational number multiplied by itself. What does that mean? Think of the number 9. The number 9 is a product of 3 times 3. 3 is a rational number. If I multiply it by itself, I get 9. Same thing with 25. That's 5 times 5. And same thing with 100. That's 10 times 10. I could continue factoring, but the idea of a perfect square is a number times itself. Hey, those are examples of perfect squares. 6, 10, and 50 are not, because no matter what I do, I can't get a number times itself. 6 is 2 times 3, 10 is 2 times 5, 50 is 5 times 10, I could do 2 times 25, but I could never get a number times itself to equal 50. So these are not perfect squares. So there's going to be two different types of square roots that we're going to look at. Square root, again, is the opposite of squaring something. The square root of 4 we can just put in our calculator. If I put square root of 4 in my calculator, I get 2. Why? Because that's 2 times 2. And so the square root is asking, what is that rational number multiplied by itself that gives us what's inside? Okay, square root of 1 is 1. Square root of 36, that's 6 times 6, is 6. And the square root of 49, that's 7 times 7. But what if we get a square root that's not a perfect square? For example, the square root of 72. Go ahead and type that in your calculator and see what we get. So you can see on my calculator screen, if I typed in square root of 49, which we just did, I get 7. That makes 49 a perfect square. But if I type in square root of 72, I get a decimal. As soon as you get something that's a decimal, you know it's not a perfect square. 72 is not a perfect square. So we get 8.49, I'll just round that, which means it's not a perfect square. So in this unit, what we're going to learn is we want to be able to write these as exact answers, which are not decimals, not rounded answers. And to do that, we rewrite this in simplified radical form. And to do that, it's all about the factor trees that we practiced in class yesterday. I want to take anything that's underneath this square root and I want to create a factor tree. So I need two numbers that multiply to 72. There's a lot of options here, and it does not matter which option we pick. You could pick 2 and 36, okay, or any other options. I'll start with that because that's oftentimes the one that many people kind of see right away, or they see that it's even and divide by 2. Just like yesterday, I want to factor this down to its primes. So I see that 6, or 36, is 6 times 6. I'm going to bring my 2 down. So now every time 2 times 36, I get 72. 2 times 6 times 6, I get 72. I'm checking to make sure that's always the case, and keep factoring until I have all prime numbers. There's a 2 times 3, there's a 2 times 3, and I'm going to bring this 2 down, and again, multiply straight across here, I get 72. It all should multiply back to whatever's inside. All of my numbers are now prime. I'm going to put that underneath my square root because that's where it is here. So I haven't changed the problem, I've just changed the way it looks. Now, think back to up here. Square root of 4 is 2 times 2 is 2, because it's a pair of 2's. The whole idea here is I'm looking for pairs. I want to pair up two numbers to form perfect squares. I know that 2 times 2 is 4, and that the square root of 4 is just one of these, is a 2. So I'm going to use a 2, get rid of this 2. Anytime I have a pair, because square root of 4 is 2, I can pull that pair outside of my square root. Okay. But I have a pair of 3's. They don't have to be written right next to each other. That's square root of 9, which is 3, because 3 times 3 is 9. So I can also pull from here a 3 out in front of my square root. Anytime I have a number that's left over, it goes back inside. Now I multiply together anything outside. 2 times 3 is 6. Anything that's left inside I'd multiply together and keep inside, and I'm done. So we originally saw that the square root of 72 is 8.49, and we just saw that we can simplify that to rewrite it as 6 times the square root of 2. Let's check in our calculators to make sure. 6 square root 2, you can see it's the exact same thing. So let's do a couple more of these together, then you're going to try a few on your own. 12, start by factor treeing. That's 2 times 6. 2 is prime, 6 is not. 6 is 2 times 3. I'm going to bring my 2 down. Put all of that under the square root. 2 times 2 is 4, times 3 is 12. It multiplies back up. That means I have all of my factors. They're all prime. I look for pairs. That's a pair of 2's. I use 1 and get rid of 1 because 2 times 2 is 4. That gets pulled outside. Square root. 3 is left over. It stays in. 2 square roots of 3. Okay. 24. Same idea. Factor tree. Wherever you start. 4 times 6. 4 is 2 times 2. 6 is 2 times 3. All of those are primes. 2 times 2 times 2 times 3 is back to 24. I look for pairs. Pair of 2's. That's a 4. Square root of 4 is 2. But this time I have a 2 left over and a 3. So when I simplify square root of 24, I have 2 on the outside, 6 on the inside, because you multiply all of that leftovers together. Okay. I want you guys to press pause and try square root of 54 and square root of 360. Unpause when you're done. So square root of 54 should simplify to 3 square root 6. It doesn't matter how you get there, but you should have 3 3's and a 2. A pair of 3's match up. You don't have any other pair of numbers, so anything left over stays inside. For square root of 360, you wind up with a lot of factors. The best way to check to make sure you haven't missed any, write them all out horizontally so you know you haven't missed any, and type them in your calculator. 2 times 3 times 2 times 3 times 2 times 5. 360, as long as you get back to the number inside, you know you're okay. Then you identify your pairs and get your answer. So we wound up having 1 pair of 2's that I pulled out, 1 pair of 3's that I pulled out, but another 2 left over and a 5 left over. Multiply the outside, multiply the inside, 6 root 10. Now, what do we do if there's already a coefficient out in front? Same thing. Okay. I simplify my square root of 27, but I don't simplify my 2. That becomes 3 times 9. 9 is 3 times 3. All of this was inside my square root. My 2 was already out in front. So again, I haven't changed anything. I just look for pairs. There's a pair of 3's. Okay. But I pull that out in front with my 2, and it's multiplication. So that 3 that got pulled out in front goes here. But I already had a 2 out in front. Left over was a 3. I get 6 square roots of 3. And pause and try 3 square root of 48. Hopefully you got to these factors with that 3 out in front. Now you have 1 pair of 2's. Pull a 2 out here. But you also have another pair of 2's, so I can pull a second 2 out in front. That 3 is left over. 2 times 2 is 4. 4 times 3 is 12. Square root 3, and we're done. Now, the last 2 I'll do real quick. This one is really no different. I really have a negative 1 out in front. So, I factor tree this as 2 times 9. That's 2 times 3 times 3. That's underneath, and there's a negative 1 out in front. The 3's are my pair. That gets pulled out in front, and it's multiplication. It's not addition or subtraction out here. It's always multiply. I get negative 3 square root 2. The last one's an interesting one. But there's a negative in there. I want you all to type that in your calculator first. In all likelihood, you got the same error message here, non-real answers. And that's accurate. This is not a real solution. There is no way that we can find a rational number that we can multiply by itself to get a negative. So anytime that we have a negative inside the square root, not outside, but inside, we state that this is undefined. In Algebra 2, you will learn a lot more about that negative inside, and you'll actually find ways to simplify this. For the time being, we will call anything with a negative inside your square root undefined.